Welcome to the CosmoQuest Science Hour. It's Wednesday, September 26, 2012. And I'm Emily Lakdawalla of the Planetary Society. Joining me is Fraser Cain of Universe Today, who's going to help me out with, I guess, the third in what's now becoming a series of updates on Curiosity.
Third time's the charm.
Third time. Well, I think the first two went pretty well. I think we'll have to see how this one goes. Anyway, this one's going to be slightly different than the last couple that we did. The last couple I was focusing on news and updates about what Curiosity had been doing recently. There's actually going to be a press briefing in a little under 24 hours tomorrow, so I'm going to be focusing a little bit less on the news from this week. Mostly Curiosity's been driving, and actually give you a little bit of a taste of what we've got to look forward to on this mission, mainly some pretty cool mountain climbing.
It's too bad we couldn't wait one more day, because there's a big press conference that all the space journalists are all gearing up for tomorrow at 11 Pacific. So
well, it's their weekly press briefing, and I guess the hints that we've gotten so far is that they're going to be starting to actually talk about some composition of rocks, which they've so far been a little bit circumspect about, because they're just starting out with their science instruments. They don't want to say anything that they're going to have to retract later. But it does sound like they're actually going to talk about rock compositions this week, which has me pretty excited. But I don't know about, not a lot of people are going to be all that thrilled about smectites and clays and versus basalt and whatnot. So I expect I'm going to have a little bit of explaining to do tomorrow after the press briefing.
You are a planetary geologist, so this is your favorite kind of thing to talk about.
Well, so anyway, what really prompted my interest in talking today was because I finally figured out the correspondence between Curiosity's long-distant view, panoramic views of its surroundings, and the orbital views that we have, the views from the top down. And so I kind of wanted to share that with everybody. I'm going to be jumping back and forth between some still images and me on the camera. Fraser Cain has warned me here that as soon as I jump to PowerPoint, he's going to immediately start snoring. So I'm going to do my best not to bore you. But this is a highly visual presentation, so I'm sorry, I am going to have to go to images.
So before we do, though, why don't we let people know how they can can reach us? So, so if you are watching this and you think you have friends and family and coworkers that'll like this, then by all means, please share this event if you're watching this on Google Plus or even on Twitter or on the event page. You can ask us any questions if you want, and I know Emily's got an agenda she wants to get through first, but then I'm sure we'll have some time to take some questions. So you can ask some questions if you're watching this from the event page on Google Plus. If you're watching this on Emily's post or the CosmoQuest post on Google Plus, or even if you're watching this on my reshare or any reshare of it, we hope. You can also, if you're watching this on YouTube, you can make a post on YouTube, and if you're watching this on Twitter, you can use the hashtag CQX, and we should be able to see it from there as well. And yeah, and we'll take, hopefully we'll take some questions after you've had a chance to bring us all up to speed.
All right. Well, Fraser's eyes are everywhere, so he's going to watch as I share my screen and show you a few, hopefully non-snory slides. So, all right, this is Mars. It shouldn't be a big surprise to most of you what Mars looks like, but I find it's useful to begin to get a sense of where it is we're actually looking at. I want you to focus on this part. We're going to go to the next slide, and you'll see here's that same little thing that I pointed out to you before. It's kind of a little sort of almost C-shaped crater-looking thing with what looks like a smoke smudge heading down to the south of it. This right here is actually Gale crater. And by the way, this is a photo taken by Rosetta during its flyby a few years ago, and that's Phobos right there, and this is Phobos' shadow. And also in this image, you can barely see it, but Gusev crater, where Spirit was at the time, is on the limb over here. All right, so here we go. We zoom back out to a whole global map view of Mars. This is a topographic map of all of Mars, with the white stuff being the highest. Here's Olympus Mons, here's the Tharsis Montes, here's the lowest point, that's Hellas Basin way down here. And if you look over here, you'll notice that there's a lot of low stuff in the north and a lot of high stuff in the south. That's the nature of Mars's topography. It's very low in the north, high in the south. They call this the northern lowlands. They call the southern bit the southern highlands. And Gale is actually perched right at the intersection of those two places. So we'll zoom in again a little bit. Here again, there's the northern lowlands. Here's the southern highlands. There's the lowest point on Mars. That purple spot is Hellas Basin. And if you look along this highland-lowland boundary, you'll see kind of a blue speck over here. We're going to zoom in on that a little bit more. This blue speck is an extremely low point on the lowland-highland boundary, and that is Gale crater. Gale's 154 kilometers wide. It's actually a pretty big crater as craters go. And it's, oh, by the way, I just wanted to zoom back out just a little bit and show you, this is where Gale crater is. Spirit, as I pointed out, was not very far away from Curiosity, but Opportunity is almost exactly in the dead center of this map, nearly 180 degrees away from Curiosity, which explains why the two of them don't actually compete for radio resources very much. Okay, so this is what Gale crater looks like in color. It's a very, very beautiful image here. We have this, it's a round crater, it's got a rim, and it has this funky mound in the middle of it. Gale is an extremely deep hole. It's about 4,500 meters below the average elevation on Mars. Mars doesn't have sea level, so elevations are a little bit odd. We're used to only thinking about elevations above sea level, but Mars, they talk about elevations relative to the average, and Gale being low means that it's the elevation of the landing area is actually at minus 4.5 kilometers. But the central mound rises 5.5 kilometers above that. That is really tall. That's more than 15,000 feet for those of you who are used to thinking of mountains in foot heights. But remember that if you're thinking of like a 14er, like I am, of Long's Peak in Rocky Mountain National Park, that's 14,000 feet above an area that's already a mile high. And this is a rise of 15,000 feet above zero. So we're talking about a very tall pile of rocks here. The central mound is officially named Aeolus Mons, but that name came after the science team had already started referring to the mountain as Mount Sharp, which is why you'll hear it being referred to by both names. Gale is an extremely old crater, and what I'm showing you here is not Gale crater. It's another crater whose name is Tooting. It's actually named after a city, as many Mars craters are. But this is a fresh crater, and you can see it has beautiful, crisp, sharp rim with landslide slumps, and it's got these amazing kind of liquid-looking ejecta all around it. And Gale doesn't look anything like that. Gale, the rim is not at all crisp. It's just lumpy and bumpy and hummocky and degraded and dissected. It's very low. This is not what the crater looked like when it was formed. It's really old. It was probably completely buried at some point. And it's been exhumed since then. There's been a really long geologic history here, and it doesn't look anything like it did when it originally formed. By the way, this crater is much bigger than Tooting. It probably did not have a central peak to begin with. It most likely had a peak ring. So what you see here, this central mountain, isn't likely related to the original central peak of the crater. Okay, so here's where Curiosity was aimed. It's a landing ellipse about 20 by 7 kilometers. It's where they figured they could get the rover to land. And here's where it actually landed, a little long and to the left. And before I zoom in anymore, I'm going to be switching from color to black and white images because this map of Gale, it's interesting. It came from images from 3 different orbiters. One of them was Mars Reconnaissance Orbiter. That's where all the fine detail of the image came from a camera called the Context Camera, or CTX. The elevation data, and this was also used to make those 3D views, that came from the European Space Agency's Mars spacecraft called Mars Express. But the color, it came from Viking Orbiter. Viking Orbiter is still the best global color data set we have for Mars because most of the other missions that have been there since then have been higher resolution data, and they don't have this beautiful global color data set that we have, like we have from Viking. But Viking's resolution is limited, so as we zoom in more, we're going to lose the color. Okay, so zooming in more, again, we see the little star is the landing site. You notice, again, here's the really degraded rim of Gale crater. You can actually see what looks like a river going into it. Isn't that cool?
So just to let you know, Emily, I don't think that your crosshair shows up very well on the broadcast. So I can barely see it, and I'm in the Hangout with you, so I wouldn't be surprised if people aren't able to see you moving your mouse around and pointing out things.
Got it. Can you see the yellow star?
I do, yeah.
Good. Okay. So anyway, if you look at this degraded rim of Gale crater that's occupying the upper left part of this image, you can actually see there's a river emptying into it, or at least what looks like a dry river valley. And that was something that happened. You got to think about what happened here in the history of this crater. It formed as a crater, it got buried, it got eroded, and then after all this history happened, it was still at a time when there was liquid water roving around on Mars, which was still several billion years ago. And that's when that river valley formed. And there are actually several valleys draining from the highlands into the interior of the crater, so it was probably filled with some sediments after all of that history had happened. So again, there's been a ton of history here. Zooming in even more, again, there's a little star of the landing site. You can begin to see there's a black streak of what are basaltic sand dunes crossing the image, and I like to look at the little landmark. There's like a little finger pointing to the north of that black streak right at the landing site, and that's what always helps me orient myself to where the landing site is on these images. Okay, now go ahead, Fraser. Do you have?
Oh, I was actually going to note that I can actually pick out the Apollo 11 landing site on the moon, because there's a really bright feature on the surface of the moon right at the point where Apollo 11 landed, and so now I can never miss it.
Yeah, that's right. Landmarks are super helpful, and like you say, once you've oriented yourself to where they are, you really don't ever miss it. And that finger pointing at the landing site has definitely helped me a lot for Curiosity. Going back to the presentation, what I have in here in green, this is a traverse, sort of what they call a notional traverse. It was sort of a path that they had kind of picked out for Curiosity, just sort of a sample path based upon where they thought it might land and where they thought it might be able to go. You can see that the path was picked out before they had narrowed the landing ellipse down to a smaller size. So it actually trails off up pretty far to the north up on the alluvial fan from that river. But you can see the path that they're going to have to take to get around those sand dunes in order to get to the mountain. They're going to have to go pretty far around to the west to cross the sand dunes in order to get up to where they can cross some of that the hummocky terrain in order to get up to where the mountain is. Here's just a few distances to orient you. A lot of people actually were confused at the beginning of this mission because people were citing all kinds of different distances between the landing site and the mountain. Sometimes you heard like 4 kilometers, sometimes 8 kilometers. It was a huge variation. That has to do with how far they're going to have to go to actually get there. So if you look at this map, you can see the red line is about 6 kilometers as the crow flies, if there were any Martian crows, from the landing site to the base of the mound where the mound starts climbing upward. But Curiosity is actually going to have to drive 8 kilometers parallel to the mound before turning and crossing the sand dunes along that green path. And I just kind of measured using these yellow sort of straight line distances. And it's actually about 25 kilometers of traverse that they've mapped out. And that number is a lot smaller than what the actual odometry is going to be, because they have to roll around all these little turns and circles, and they're going to roll back and forth from places where they're going to do measurements. And so it's probably going to be 35 kilometers for the whole tour. But even if it was 25 kilometers, they'd have to average about 250 meters a week in order to cover that whole distance in the nominal mission.
Well, how does that compare to Spirit and Opportunity's drives? I mean, they've both done, what, 25 kilometers or so?
Well, Spirit hadn't gone that far. Opportunity has made 35 kilometers over its 8-year mission, but you have to remember that Opportunity has uniquely easy driving terrain, and that on some sols it actually managed as many as about 300 meters of traverse distance. And that may happen for Curiosity during that part, that 8 kilometers that they're driving parallel to the mound in order to get to that sand dune terrain. But after that, I think it's going to be a lot harder to average much more than 100 meters a day, because it's difficult terrain to drive through. And so what that tells me is that they're probably not actually going to cover that entire traverse distance in the nominal mission. And so it might make you wonder, well, how are they going to be able to accomplish the mission that they went to Mars to do if the drive distance is that high? And I'll answer that question in a few minutes. The answer is yes, because they don't actually have to drive as far as that map shows in order to accomplish their mission.
But they definitely don't want to drive across those black sand dunes, right? I mean, that looks like it's the quick way, but that's the death way.
That's right. I'll show you at the end of this. I'm going to jump away from my PowerPoint and just wander around a high-rise image, and I'll show you what those sand dunes look like at really high resolution. Okay, so we zoom in some more. Oh, right, so this is really zooming in. What you see here is actually the view from Curiosity. This one was taken, I believe this is a Sol 19 panoramic view of the mound, looking almost due south, and you see these beautiful, beautiful buttes and what they call yardangs. Look up yardangs, Yardangs, and stick in the word China, and you will see some amazing rock formations in the Mongolian desert that look strikingly similar to these guys.
That's right. We talked about this last time, right? Where you get this wind that's blowing, and the wind is actually carving these almost wing-shaped, features right into the rocks. You can actually see almost like the rocks are becoming aerodynamic.
Right. They get this teardrop shape, and then because the layered rocks have slightly different resistance to erosion depending on the layer, the wind sort of carves out and picks out little layers within the rock and gives them the beautiful stripy kind of appearance that you see in Curiosity's distant views.
And I guess here on Earth we've got water and plate tectonics and things like that can sort of shape the landscape. But really on Mars they've only got wind.
Wind and time. And the ingredient
yeah.
that Mars has that Earth does not is, like I said, we're looking at maybe a billion years of erosion. Even if it's a few 100 million years, that's not very long geologically speaking, but it's really long for wind to have to act on a terrain. So here's just one mast cam picture of this terrain. It's just so lovely. There's all these layers that you can see. And I spent, if you follow me on Twitter, you'll know that I fell down a rabbit hole yesterday trying to figure out how these things correspond to each other. What you have on top is a view from CTX that I've kind of warped in order to, it's polar deep projected in order to make it so that straight lines from Curiosity's panorama from the surface will connect directly with features visible in the orbital view. And you can match things really beautifully. All the little pointy peaks can be connected straight to pointy features that you can see in the orbital images. It's just lovely. But most of these pointy peaks, I want to point out, happen in this upper part of the mound, not in this lower area. And that's kind of important because if you look at the traverse and you compare it to the area that Curiosity can see, there's only one little part of the traverse that we can actually see from where Curiosity is sitting. And that's the part where it turns and heads straight up in a gap between two pointy hills. We're looking almost straight up that valley. You can see it as a little dark kind of dash going vertically in the very center of the panorama. Almost all of the rest of the traverse is actually hidden from view behind what they call a light-toned ridge that's closer to the foreground. And so here we are. Now we're back on the context camera view, so we're looking straight down from orbit. We're back, north is up, the mound is to the south of us. And you can see how this traverse kind of curlicues around the dark sand dunes and that light-toned ridge. And here's where I'm going to end. I just want to point out that that Curiosity has, that the science team has really mapped this area in detail, looking at the high-rise photos. And where the exciting bit is in that blue text, the phyllosilicate-bearing trough. That is where the very oldest rocks are. And that's where Curiosity is really, we really hope that Curiosity is going to hit pay dirt. So as soon as they manage to cross that light-toned ridge, that's where they're in the deepest part of Martian history that they have, that no rover has ever visited before. And that's where the geology is going to get extra exciting.
So, I mean, can you expect them to spend a lot more time in that area if they find some interesting stuff?
Well, definitely they'll be spending time, and they'll certainly be doing several samples in there. But the whole goal of this trip is going to be to kind of do geologic mapping as they go. And fortunately, they're going from the very bottom of the mound to the top of the mound. And as the law of superposition states, the oldest stuff is at the bottom. Anything that overlies it must necessarily be younger. So you're getting to read the history of Mars from the earliest, the earliest part of the history up to the latest part of the history. When you get into the very latest bits, what they call the dark-toned layered yardangs, which is that stuff that looks so dramatic in the view from where Curiosity landed, that's actually later in Mars's history. That's around the time of the rocks that Spirit and Opportunity has investigated. So it'll be really interesting to get to those rocks because we'll be able to compare to what we learned in other places, other locations on Mars. But the unique rocks for Curiosity are going to be the ones that are actually below all of that most dramatic topography. So I can do a couple things now. I can start to take questions, or I can take us on a really high-resolution tour of a high-rise image that crosses a lot of this interesting rock. What do you think I should do at this point, Fraser?
Well, I think I know what you want to do.
Well, shall we then? We'll go up to.
Let's see this. Let's see these pictures. Yeah.
Yeah. Instead of looking at PowerPoint now, I'm actually going to a tool called HiView, which is the software that was developed by the HiRISE team at the University of Arizona. HiRISE is the camera on Mars Reconnaissance Orbiter that is able to achieve 25-centimeter resolution on the surface of Mars, and the images that it produces are freaking enormous, and you can't even open them in Photoshop most of the time. So they're served in a format that not very many people are familiar with. It's JP2 format. It's like a second-generation JPEG format. And the way that that one works is it's pyramidal, which means that you can download just a little bit of the data to get a really zoomed out view, and then as you zoom in, you only have to download the bits that you can actually see on your screen. So it's a really great way to serve huge data sets that are available kind of live in a browser, rather than having to download a couple of gigabytes of data in order to be able to scroll around the thing in full resolution. So I'm going to screen share HiView, and this is just one high-rise image of the landing area. And again, here's that light-toned ridge, and behind it, this is the phyllosilicate-bearing trough that they're most interested in. But first, let's zoom into those sand dunes, because that's some of the scarier stuff, and we have
and
to
just
wait.
To let you know, your mouse is coming through this time, so
Great.
So we can see it. Yeah.
Now, one thing that we do have to do as I talk is that we are going to have to wait for it to download. I'm going to get right up to full resolution here, and so you can see that there's. It might be kind of hard to see actually at the resolution of the webcast, but the fact is that this area looks pretty featureless because we're looking at basaltic sand, very dark sand that is going over bedrock in this area. And you can see bits of bedrock are poking through, but most of it is, you can see just a little bit of sand ripples here and there. The traction for Curiosity, even though she's got bigger wheels than Opportunity had, she exerts about exactly the same amount of pressure on the surface, bigger wheels, bigger weight. And so the rover has basically pretty similar traverse capability to Opportunity. And what that means is that you can get to slopes up to like 20, 25 degrees if they're on solid rock. But if you're on sand dunes, you can only manage a slope of about 15 degrees.
Now, somebody asked on YouTube if HiView is available to the public, and it is, right?
Oh, absolutely.
Yeah.
So anytime you go to any picture on the HiRISE website, there will be a link there to download HiView. It's a pretty small Java-based application, I think. And then all you have to do to use it is you find any link to a JP2 image on HiRISE website, and you literally drag and drop the link into HiView, and it immediately opens it up, and it's spectacular.
Yeah, one of my probably favorite things that I'll look at is the images, the raw images that come out of HiRISE every day. You can subscribe in your RSS reader or just go to their website. And like today, I don't know if you saw the pictures they put out, was it today or last night? Just some amazing features, some amazing photographs. So highly recommended. And there's so many pictures that come out of this service that we don't have time to report on them all. And so I highly recommend if people want to see them.
I don't have time to report on any of them. And the fact of the matter is that they produce so many pixels that odds are good that you may be the second person ever to look at the pixels in that image, because they're just so huge that no one person can look at all of them.
I'm going to find one right now that just blew my mind, and I will share it in a second when I find it. But yeah,
go
keep
for
going.
So I'm going to zoom out again, which you absolutely have to do in order to find your way around these images, because you get lost in the details. And so one kind of interesting thing about these basaltic sand dunes and the bedrock that they're found on top of is that they've actually, because it's sand and they're active sand dunes, they're getting blown across the surface of Mars all the time. They scour the surface, and so the places in between dunes where there isn't actually any sand right now are some of the cleanest rock surfaces in Gale crater. So if we look at that, here's an example of an interdune area, and you can see there's a lot of rather interesting geology going on here. There's little polygonal cracks it's really cool terrain. And so even though this is not precisely the rock that Curiosity has been sent to go look for the evidence of ancient water on Mars, I'm sure we're going to stop here and do some sampling and some investigation, because it will be some of the cleanest bedrock, flattest area for driving on that Curiosity will have. Have you found your image yet, Fraser? Let's see. I'm going to scroll around this a little bit. Okay, so here's that light-toned ridge, which, as you can see, it's got a fairly shallow slope going to the north. So the direction from which Curiosity is looking at it right now, it sees a very, very gentle hill. But the far side of it, the southern side, which Curiosity can't see, actually has a pretty steep drop. And it's behind that drop that the phyllosilicates are located, and that's what Curiosity is really going to be interested in seeing. So I'm going to go down there a little bit to some of these phyllosilicate-bearing rocks and zoom in. And we have to wait for it to download. And again, we see this interesting polygonal cracking. It's fascinating. It's really fun to just to download, to bring up one of these images and download it, and just wander around, zoom in, zoom out, see what other kinds of landscapes you can find.
All right, did this come through? Did you get this?
That did come through. So let's go ahead and go over to your image.
So this is Lukey Crater in the Southern Highlands, and it's a crater formed on the floor of Uzboy Vallis between Hale and Holden craters. But like, these are the kinds of images that you're seeing every day, and it's just a river of images that just flow past. I don't know what to do. I just, I look at it and go, I should write a story on that. So busy.
What I like to do is I like to go to the I like to go to the archive, and they have, like, they'll show you, I don't know, 25 images on a page, and you can hack the URL to just pick a page at random, like page 726, and then you'll be looking at images that, again, likely nobody has looked at, just a couple of people, and every one of them is amazing. They all just reward close attention.
But you can imagine, right? You can imagine some Martians looking at high-resolution images of Earth and kind of saying, "Whoa, look what I found over here! Look at these pretty pictures of, of this, I don't know, river or whatever." Like, it would keep people busy for a while.
It would keep people busy for a very long time. That's right. Yeah. Well, Mars has about the same amount of land area that Earth does, thanks to the fact that it doesn't have oceans. So
someone just asked. So if you go to the So Guido Bibra on Google Plus just asked me where I'm getting those images from. So if you go to if you do a search for HiRISE, HIRISE, that's the name of the experiment on the orbiter, and then they have an RSS feed from that site that you can subscribe to, and then you get usually about 4 images a day, which is a fraction. I guess it's the favorites from the HiRISE team, and it's just a fraction of the total images that are coming to you. Yeah, people don't want to see my RSS feeds. I have so many RSS feeds I subscribe to.
Yeah, those are probably the ones that they take the time to caption, but they release everything within. It's not immediate like it is with the rovers or Cassini, but then it's not raw images when they release them either. So it's the full-on science data that you're getting, and I don't know what the release delay is. It's like 1 or 3 months or something like that, but it's a fire hose of data, and I don't actually use the RSS feed. When I'm ready to go look at some HiRISE images, I just go to hirise.lpl.arizona.edu, and I just wander around.
Yeah, so I get a couple of images a day, and sometimes one of them piques my interest and we'll do a story on it.
So I'm here again. I'm still in this phyllosilicate bearing trough, and I do want to point out something that's a little interesting. So I've applied an automatic contrast stretch to the image, which stretches each of the color bands differently. And what that does is it emphasizes subtle color differences. It also makes the basaltic sand dunes, which are black, and makes them look blue. And when you have blue, ripply things lying in local topographic lows, every conspiracy theorist on Earth thinks that these are lakes on Mars, and they are not lakes on Mars. They are basaltic sand dunes where the color stretch has made them look blue, and they have ripples because they're sand dunes.
And they're blue.
And they're blue.
Blue ripples. I see a sailboat.
Right, and actually what's kind of funny about it is that they look, especially from a distance, they look really similar to some of the black, low elevation filling terrain on Titan. And on Titan,
I was just going to say that, yeah.
There are actually lakes in the near the poles, but most of the stuff on Titan that looks black and fills topographic lows is also sand. which is, I think, just a bizarre and interesting parallel. Okay, so we scroll back out a little bit. Gosh, this stuff is beautiful. And we
But
go
this
down.
is the point, as you said. This is the pay dirt, right? This is the area.
That's right.
And get used to that. I mean, that lake on Mars. I mean, you can see it in the lower resolution images. That's going to be one of those features that you're going to see time and time again, and that should help you orient in the future when you see it, because.
And you see these. There are larger areas of sand dunes. This one really looks like a lake with little islands poking through. And again, this is just a topographic blow that's filled with very dark sand. The dark basaltic sand very likely comes from outside Gale crater entirely, and lighter dust can be carried back out of Gale crater, but the heavier the sand grains are left inside. At least that's the hypothesis I've heard. Of course, people go to Mars with all kinds of hypotheses, and they all turn out to be wrong when you investigate them with the rover that's actually on the ground. So I'll be curious to find out what we can actually say about the sand dunes later.
But if you could stand on it and maybe hold it in your hands, would it be like a black sand, like a black sand beach?
Yeah, it would. Sand, even when it's saltating in a jumping around, being blown around in a thinner atmosphere on Mars, it's still fairly similar to what you would find on Earth. The atmosphere is less thick, but it's also lower gravity, and the two kind of balance each other out just a little bit. So you do wind up with a material that has a really similar texture to what you find on Earth. And of course, even on Earth, you have a lot of variation in sand grain sizes depending on the energy of the environment that's moving it around. I'll just scroll a little bit further south and get out of that phyllosilicate-bearing trough to these yardangs, and especially to this feature right here, which is so cool. It looks like a river valley, and it is. This is a, oops, I need to share my screen. Hold on a second. Okay, so we're a little bit to the south of that phyllosilicate-bearing trough, and this looks like a river valley because it is. It used to drain with water. You can even see meanders and all kinds of stuff from the higher part of the mound. And so that's definitely one of the things that Curiosity is going to investigate. But it's not going to be easy, because let's go back to the north a little bit and see what happens to this river as you go north. And it keeps on moving out. Now it's coming out of the valley, and I don't know if you can tell, but the topography has completely inverted. So what used to be a valley up here, and you can see that it's dark on this side. The shadows are on the are to the southeast. So we've got a valley here. Now we go back to the north again, and you can see it's now dark on this side. It's become a ridge, and this happens a lot with Martian with Martian valleys, because the valleys were filled with some kind of sediment that became lithified, and that sediment that turned into a rock was more resistant to wind erosion than the stuff that the valley had originally formed in. And so as the wind blew on this thing over the eons, millions of years, it blew away the less resistant stuff, left the more resistant stuff, and so you actually get kind of like a fossil cast of what used to be a river system, preserved, raised up above the surrounding landscape. And Curiosity has to cross this somehow, but it can't cross it down here. It has to go up a little ways, get to where the topography is relatively easy to deal with, and actually cross at a higher elevation of the valley. So all in all, I highly recommend scrolling around some of these images. I'll see if I can post a link to a couple of the more interesting ones with some basic instructions for how to use high view to see them, and hope you guys can enjoy it.
So why don't we sort of get prepared and start taking some questions. So we're going to be, so if you want to ask any questions, you can reach us either, if you're watching the event page, you can post a question there. If you're watching the actual Google Plus page from Emily's original posting of it, or my reshare of it, you can post a question there. If you're watching this on embedded somewhere, you can ask a question on Twitter. Just use the hashtag #CQX. That was redundant, wasn't it? Use the hashtag CQX, and or if you're watching this on YouTube, you can just post a question into the comments on YouTube, and we should be able to spot them all. So you can all take a second to organize your questions. Ask your questions about the rover, about the sort of what's coming next, about your conspiracy theories, and we'll try to get through them. So what's coming up? I mean, we've got the and just sort of give people a bit of an update, right? We've got this rock Jake on the surface of Mars, and Curiosity has blasted it with a laser now.
Yeah, so Curiosity's actually blasted quite a few rocks with the laser, and that's the wonderful thing about that laser instrument, is that you can just be real trigger happy with it. You're not using up any resources, and you can reach rocks that are quite a distance away. I think the number is 7 meters is the nominal distance that they're supposed to be able to reach and see. It's not the most detailed view of the composition, but it gives you a really good reconnaissance as to the composition of a rock and to decide whether or not it's worth going up to with your in situ, what they call a contact science instruments, which include APXS, the alpha particle X-ray spectrometer, which can read the elemental composition in really high detail, and the MALI, the Mars Hand Lens Imager, which is just a wonderful camera. It's produced some really amazing pictures, and I do plan to post a lengthy post on all the contact science that they did on Jake Matijevich after they do the press briefing tomorrow. One thing I learned this morning that was kind of fun is that they shot several views of Jake as they were leaving it behind, and in order to do that, they drove backwards, which is something that they do all the time on Opportunity because they have to, because it sort of equalizes the lubricant inside the wheels. It's something that they discovered that they had to do in order to preserve the health of the wheels. Curiosity doesn't have the same kind of motors that Opportunity does, so should not ever need to do that. But it's nice to know that they can sort of drive backwards, take their backward-looking view, and see the thing sail off into the sunset, which is more or less what it did.
So a couple questions. This one comes from Alan Curlin. So with all the sedimentary layers, are they going to have problems getting up the steps? So, is that what we're going to see the features look like? Is it going to be like a smooth transition? I mean, I'm thinking like places like Moab, where you've got just these beautiful, smooth, almost like, I don't know, like water-shaped, like wave-shaped rocks, and there are layers, but the layers blend smoothly from layer to layer. Is that what we're going to be seeing, or will there be, if it's different kinds of structure, you can imagine it weathering, eroding in different ways. You've actually got steps.
Yeah, it depends on where you are in the sequence. It looks to me like the material that's in the phyllosilicate-bearing trough area is more like that smoothly eroded sort of terrain that you're talking about. In detail, it's always going to be picking your way around rocks and ridges here and there. It's always a challenge to figure out how to navigate the rover on Mars. But as you get up into that steeper terrain where the yardings are, it does get more difficult. One thing that they are going to be doing, however, is they're not scaling any of those hills themselves. They're just going to be crawling up valleys in between them. And those, like valleys on Earth, should be collecting sediment and gravel and things that make the terrain perhaps slightly more slippery, but it's also smooths it out, so it makes it easier to drive long distance on it. But I think it remains to be seen how easy it's going to be to traverse each of those terrains, and each one of them is going to be slightly different.
So, question from Time to Wander 70. So, where is the water now on Mars? Where do we think it is right now?
There's a lot of it. So there's a lot of water preserved that you can actually see from Earth with a telescope that's in ice at the poles. And
yeah, the white stuff on the top and bottom of Mars in the pictures is water, yeah.
And also you can see white clouds covering regions of Mars during certain times of the year. And again, that is water ice cloud. And the water, Mars kind of breathes because it has seasons just like Earth does, and it has these polar caps. And when the polar caps are exposed to the summer sun, quite a bit of water sublimates from the ice cap into the atmosphere, and you get this motion of water from the North Pole to the South Pole over the course of the Martian year. And there's evidence that Mars's axis tilts to a lesser or greater extent with time, just like Earth does, but Mars isn't stabilized by the presence of a large moon. So while our axis tilts less and more by a couple of degrees here and there, Mars's rotational axis may actually tilt nearly sideways at some parts, every couple 100,000 years, and then it goes nearly upright. And during those times when it has a more Uranus-like tilt, there may actually be periods where the pressure of water in the atmosphere gets high enough that you can have stable liquid, little tiny bits of stable liquid near the poles during some times of the year on Mars. But those polar caps, you can actually kind of think of them as continuing underneath the surface of Mars.
Right.
So the ice is stable at the poles because it's so cold there, and because it's in direct contact with the atmosphere. as you get warmer, it's no longer stable, but the ice table kind of dives underneath the surface, and huge areas of the Mars northern lowlands actually have a ton of ice very close to the surface, as Phoenix found out when it landed. Now, we knew already from measurements from neutron spectrometers that the hydrogen was very likely there, and very likely it was in the form of water before we sent Phoenix down there. And Phoenix, ground truth that confirmed that there was indeed ice. But there's actually ice that you can detect with these neutron spectrometers going quite far south in latitude. And there's even a suggestion that one of the Viking landers, if it had only dug like 10 centimeters deeper, would have encountered the ice table itself. So that would have been quite a shock. And it's kind of unfortunate that it didn't happen.
So, I mean, you can't, I mean, based on sort of what we found with Phoenix and what you said with Viking, do you think that there's a water table across the whole planet?
There sort of is, yeah. I mean, if you dig deep enough, you can get to water, frozen or not, just about anywhere under Mars. And there's some wonderful parts in Kim Stanley Robinson's Mars books where he talks about doing deep drilling to access high water under pressure beneath the ice table, and it's all somewhat plausible.
And so dangerous, I recall in the books.
Yeah, it was quite dangerous. Well, everything turned out to be dangerous because humans were so bad.
Yeah.
But yeah, so there is, just as on Earth, you can drill just about anywhere and eventually you'll get to water. On Mars, it's somewhat similar, although in most places you're getting to ice, not liquid water. And of course, it would behave quite a bit differently if you manage to get in contact with the low pressure atmosphere and the low temperature atmosphere. But there's water all over the place. And I think now there's an interesting debate going on in the scientific community about what happens as Mars's climate varies, whether that water gets mobile enough to actually crop up on the surface and do anything interesting, whether there are liquid water, even in tiny little films on grains in near polar environments that actually can exist for a really long period of time so that you could have extant modern life in some of these environments. It's still hotly debated, but they aren't kooks who are debating this kind of stuff. It's mainstream science.
So I'm going to share a picture again. So see if that comes through.
Yes.
You see this?
Yes, I can see that.
And I'm going to try, I don't know if I can zoom in on it. My computer is not happy right now. Let me see. Yeah, here we go.
Yeah.
So this relates to a question that I just got. So someone asked, so Robert Scott Herrick said, I saw a picture of Phobos today, and have we seen Deimos from the surface of Mars? So this is important. So this picture was released just recently, and you can see it. I know it doesn't come through, but you can see this. You can see like the shape of Phobos, and this was taken during the day, and it shows. You can see almost like the moon, on the Earth shine, sort of reflecting off of Phobos, and you can see the part of it that's illuminated. It's just a stunning picture. When I saw, I couldn't. My jaw dropped when I saw this picture. So, have we seen Deimos with the same level of kind of resolution, or from Curiosity yet?
Well, no, for a couple of reasons. First, let me explain a couple things about this image that you're looking at right here. You are seeing a crescent Phobos. It's what it would look. It's very similar. Imagine a waxing crescent moon. In our own twilight, this was taken actually a few minutes just after sunset. So it's in a very, very bright dusk, but the sun is actually below the horizon. And you have the limb of Phobos looking down at the sun that is just set. And you can see that Phobos's limb is very lumpy and bumpy, as it is. It's a lumpy, bumpy moon. It's quite small. And you can see the terminator is also lumpy. My brain really wants to see a small crater being outlined on the terminator, but I am pretty certain that that is a JPEG artifact. And so that once we get the really nice data from Curiosity, which I understand is not on the ground yet, that will probably go away. But it's quite true that you can see the shape of Phobos in this image. There's never been an image like it before, and it's just really stunning and stirring, I think.
Yeah, I saw that, and like I said, my jaw dropped. That is one of the coolest images. And the resolution's a little low, but you get this glimpse and a hint, knowing from when we see the moon in the sky, you kind of see it and go, oh, wow, that is fantastic. Yeah.
So to answer your question, we have not seen Deimos like this, and I think that if we try to do it, we may be able to see it as a smudge, but Deimos is half the diameter of Phobos and also quite a lot farther away. And because the two of them orbit so close to Mars, the range to Deimos changes a great deal depending on whether it's straight over your head or if you're sighting, along the horizon at it. And so we may be able to find it in a Mastcam image, but it's gonna be a little white smudge. It's gonna be very small. However,
it's not as close. I mean, it's a lot further and smaller.
But we have seen both of them actually fairly clearly as they are silhouetted against the sun, because both of them are in basically equatorial orbits, and Curiosity and Opportunity are both in nearly equatorial locations. So it happens pretty commonly that there are transits. Happens twice a year. There are many transits of the sun by Phobos and Deimos. Phobos actually crosses the Martian sky more than twice a day. It orbits so fast it actually outpaces Mars's rotation, rises in the west and sets in the east, rises in the west again every 11 hours. So it's really fast. Deimos orbits just a little bit slower than Mars rotates, so it stays up in the sky for about 2.5 Martian days before it sets.
Yeah, I mean, the Phobos' speed is actually kind of suicidally fast.
Yeah.
It's going to be gone in about 10 million years. Okay, well, a whole bunch more questions now. They're coming in fast and furious, so we got to... with those basaltic sand dunes, Ilya B wants to know how fast they move. Do they move?
They do move. They have actually been observed to change position very slightly from Martian year to Martian year. And so one of the things that I know, in particular, Mike Malin, the guy who's the principal investigator on the Mastcams, is super interested in modern changes on Mars and also in sand dunes. So you can bet that they are going to be doing some really close investigation of these sand dunes, whether they can be observed to move as Curiosity is standing there. I'm sure they're going to be investigating the sand grains up close with the hand lens imager, and we'll try to watch grains move with time. Remember that both of those cameras, unlike the previous cameras on previous Mars rovers, these things are actually capable of video. It's not full, 25 frames a second. It's somewhere around 3 or 4 frames a second, but it's video, and they'll be able to actually watch things moving. So that is going to be rather exciting to see. But I should point out that Opportunity has also seen sand move while it's been sitting there on Mars. There's actually one really cool day where pretty recently, it was driving down the east side of Cape York, and you can see the tracks that both rovers leave behind as they drive, because they disturb the bright dust, and you see the darker material underneath. And the tracks disappeared like just several minutes later. It was really cool. And so you really get a sense that things are actually in motion. Mars is, that there hasn't been a lot of change there over the last billion years, but there is change, and it is a dynamic and living environment.
It would be really, so Michael Jobin made a comment that I know is going to hit you where it hurts, which is he says that he's kind of disappointed that there wasn't a microphone on the rovers.
Yes, as am I.
Yes, and in fact, you and your boss lobbied heavily for the possibility of a microphone showing up on Curiosity, and it would have been very helpful for things like listening to the wind and listening for sand grains and Martians and all kinds of things.
Yeah, and quite honestly, the engineers would love to have a sound, a microphone just to listen to it's amazing what you can diagnose in a system that's having trouble just by listening to it.
That's a really good point. I never even thought of that you could listen to Curiosity itself, yeah.
So yes, we continue to campaign. We may not have done it on Curiosity. We're working really hard on getting it on InSight. And for a seismological mission, it would be great to have a sensor that could tell you when the wind was blowing and how hard, because that kind of information is actually extremely important to help correct your seismological data for what's going on the surface, taking that out and understanding what's going on underground. So they haven't said no yet. They haven't said yes yet. Well, we are working on it.
I've seen iPhone apps that'll tell you how fast the wind is blowing based on the microphone. So,
well, it's funny that you mentioned that, because Phoenix had a descent imager that was basically based on an off-the-shelf cell phone camera, and because it was an off-the-shelf cell phone camera on an off-the-shelf cell phone camera chip, it had a microphone. And they didn't wind up turning the stupid thing on in an event that frustrated both us and.
Okay, we're getting you riled up now, Emily. Yes. So I will wait 2 weeks, and then I will bring it up again.
Excellent.
But at least you can pass along the feedback to people that the general public, without any prompting, has been dying for a microphone.
Yes, we know.
It's good. It's good public relations.
Yes.
So Eric Jones asks a question: what are the future aspects of mining on Mars? Would there be resource deposits in the same way that we find them here on Earth? Would future miners be able to go and find veins of ore and mine them out to, build their shelters?
Well, yes and no. Yes, because a lot of mineral environments on Earth are places where there has been volcanic activity with high temperature, acidic groundwater circulating, dissolving certain cations and redepositing them as highly concentrated ore minerals in other locations. And all of that definitely describes environments that we have seen on Mars. So those kinds of deposits are certainly there to be found on Mars. There are some other kinds of minerals, the kinds that you find in the sort of fluids that form inside granitic plutons. These are kinds of volcanic rocks that happen in a really highly evolved tectonic environments on Earth. Granites contain all kinds of crazy stuff, from lithium all the way up to the rare earth elements and the platinum elements and the plutonium and stuff like that. So some things will certainly, certain metals like things like lead and iron and nickel, all the kinds of stuff that you see kind of in traditional miners wearing hard hats and pickaxes. You should be able to see an awful lot of those things on Mars, but some of the other stuff, the stuff that's associated with really deep-seated granitic type minerals, you're not so likely to see.
And probably no diamonds, because they're organic, right? They'd be coming from carbon deposits.
But of course, Mars has carbon because it comes in from meteorites. The carbon has to be really deeply buried and subjected to incredibly high pressures, but they come up in these volcanic kimberlite pipes. So I don't think that's an environment that exists on Mars, but I have to say that I am not an economic geologist, so that's something that I would have to defer to somebody who knows more what they're talking about.
Oh, okay. All right. Well, I thought I'd solved it, but okay. Okay, so this question comes from Andrew Planet. Could water delivered to Mars by crashing water-laden bodies from elsewhere in the solar system remain stable on the surface as to terraform it? So can we terraform Mars by smashing comets into it? I believe that is the plot of a couple of these books we've read.
Yeah, I think that the approach of trying to fill the atmosphere with more, make the atmosphere denser, so you set up a greenhouse, seems to be more promising than wandering around the solar system, finding Mars-crossing comets and changing their orbits enough to crash them into Mars.
So you just like run your chlorofluorocarbon factories 24/7 to improve the greenhouse effect.
Yeah, you make some intense greenhouse gas that is able to trap heat and make water more stable, and that'll set up the whole, it'll make it run away, and all of a sudden you'll have a paradise on Mars for everybody.
But I know the problem that you have with Mars is that because Mars doesn't have a magnetosphere the way that Earth does, it doesn't have any protection from solar radiation, from solar wind, and from things like that, and so there's this constant buffeting from the sun that's trying to sort of siphon away all the lighter minerals, so the lighter elements like hydrogen. And so if you do seed the planet with tons of water, the sun is just going to try and blow it all back away into space.
That's true, but that's a process that happens over geologic time, and humans just don't care about geologic time.
Just crash the occasional comet back into your planet and you should be fine.
Right. I mean, it's a relatively fast process, geologically speaking, but it still takes thousands of years to, or more, tens of thousands to operate. And so if we can make it work for a decade, that's all humans care about. That's as far forward as anybody seems to ever look these days.
Yeah.
And by the way, we have reached 5 o'clock, but I can stick around for another 10 or 15 minutes easily. So I'm
sure.
good with that, if you can.
A bunch more questions. Okay. Let's see. So Tim May asks, so since there are clouds on Mars, can it theoretically rain? Or perhaps could it snow carbon dioxide?
You get carbon dioxide and water frost. There was a really cool thing that Phoenix observed where it was looking at some very high altitude water ice clouds, and it found, now I'm forgetting what the term for it is, but basically it started snowing, but it was snowing at a very high altitude, and after a certain point you get to a low enough altitude where the temperature gets high enough, the pressure gets high enough that the snow it transpired back into water vapor. But Phoenix had this LiDAR system, so it pointed a laser up and looked at the scintillations to see what it could see, and it was able to detect these basically snow crystals in the sky, and they fell a certain distance and then they disappeared again because they evaporated away. But it does snow on Mars, and you don't really have to imagine a very big change to its climate in order to make that snow get all the way to the surface.
Well, I mean, we see the size of the actual polar ice caps changing over the course of the season, so somehow that water's getting there, right? But it's coming straight out of the atmosphere, isn't it?
Yeah, it's mostly, as far as I understand it, it's frost coming out of the atmosphere. But again, you're going to have to ask a meteorologist that one. I actually know a Martian meteorologist. He's the guy on the mission who's been sequencing these really cool observations of Phobos. He's also the main El Numero Martian astronomer. His name is Mark Lemon. He's at the Texas A&M University, and he was the chief of the camera team on Phoenix and is a member of the science team on Curiosity.
I wonder how one becomes a Martian meteorologist.
Well, you become an Earth meteorologist first, and then you see if you can glom your way onto a Martian mission. There's somebody on Twitter. Her name is Carrie on Mars, who is she was Mark Lemon's student. I think she's now a postdoc, and she's also working on the Curiosity mission. It's kind of fun to follow her tweets as well.
So Evan Fleshig asks, we talked about the absence of large moons around Mars. So does Mars have any tides?
Does Mars have tides? That's an interesting question. I don't think so, because the only thing that would exert tides is something near enough to
Phobos.
Yeah, Phobos is just way too small, and it's not tidally locked to the sun. So no, that's a good question, and I think the answer is no. There should be no detectable tides on Mars.
But the Earth has tides from not only the moon but also from the sun. So,
yeah, that's true.
And I forget what the ratio is. It's like 90% from the moon and 10% from the sun or something like that. So you could imagine, but then there's no liquid, there's no water for it to necessarily. So, but I know tides, like here on
tides
Earth,
affect the rock as well.
That's right. Yeah.
Mars is a lot farther from the sun, but its gravity is lower. It's stiffer than Earth is because it's colder. It also has Jupiter a lot closer. So I mean, probably there probably are tides. I'm not sure if they're measurable or noticeable, but now you have to ask a geophysicist, and I know several Martian geophysicists as well.
Well, then encourage them to hand that out as an exam question.
Yeah.
Calculate the tides of the ground because I know here on Earth, right, we're actually rising and falling a couple of feet over the course of the day as the moon moves around because of just the tides from that. So yeah, it would be, I guess, calculatable.
Ask Randall Munroe on his new What If comic.
Perfect. Actually, those are great. I really like that. That's the guy who does XKCD, and he's got a whole separate comic called What If, and he graphically goes into really puzzling questions.
My favorite one recently is, what if all of the water in a rainstorm fell as one large drop? And the results were really quite devastating.
Well, water is so heavy.
Yeah. And there's a lot of water in a rainstorm, as it turns out. Anyway, go on. We're quite
okay. So Doug Rao asks, and I think this is going to be our last question for the day. So Doug Rao asks, are all those small circular features in that old bedrock that we saw, are those small craters? Remember that one that we're calling this lake? I'm sure it's going to get a name at some point. Is that an impact crater?
Yeah, if you see a circular feature, your first assumption should be that it's an impact crater. But most of these things are extremely old impact craters that were once buried and have since been exhumed. The same is probably true for a lot of the craters that Opportunity is seeing. It kind of depends. You can tell a fresh crater, and there are a couple of fresh craters in the region around the Curiosity landing site, but the vast majority of what you're seeing are really super old craters. They're basically fossil craters.
Cool.
Yeah.
So, well, why don't we wrap this up then? We've kind of hit the hour mark. So, thanks for your time. What's next? Oh, we're going to do the Weekly Space Hangout tomorrow.
That's right.
So that's Thursday, 10 a.m. Pacific. We'll be doing a roundup of all the big space and astronomy news here on Google+, same format. You can go, if you go to the events, you'll see all the other events that we have planned. And then if you are like super nerdy about this stuff, tomorrow at 11 a.m. Pacific, NASA is going to be doing a mission briefing and sort of update everyone on the mission.
And you really don't have to be super nerdy to appreciate those, because they are pitched at maybe not quite a mainstream media, but a pretty close to a mainstream media level. So, and typically you have John Grotzinger in these briefings. He's a project scientist, and he just cannot not be a geology professor. So he'll sit there and he'll give you a lecture about how the sedimentology works, and it's really quite enjoyable to listen to him talk, because all of a sudden you're in the classroom. It's kind of amusing.
Yeah, and I mean, honestly, that's what we as the reporters, that's all we're doing. We're watching, we're getting the news out of them, we're digesting it and presenting it out onto the internet. So you can just skip us and go straight to NASA if you need to. Yeah, but great. Well, thanks for having me, Emily.
All right. Well, thank you, Fraser, very much for your help as usual. You are certainly much more knowledgeable about how to make all of this social networking black box stuff work than I am. So thanks very much to Fraser Cain of University. I'm Emily Lakdawalla of the Planetary Society. You can find me blogging most of the time at planetary.org/blog, where you'll also find lots of other really interesting voices from around space exploration that I'm trying to get more different people talking on the blog. So check us out, planetary.org. Thanks, Fraser, and we'll do this again in a couple of weeks, I think.
In a few more weeks. Okay. See you later.
Cheers.